This is a talk on regular expressions. My name's Chris Mountford, and I gave this talk in Sydney at Atlassian's offices down in the basement. I thought I'd start with a little cartoon that gave me a giggle, and it's on the topic of saving a day with regular expressions. And of course, if you're an expert in regular expressions, you'll know that feeling of swinging in on a rope and tapping a couple of lines of Perl to save the day. And the title of the talk is Now You Have Two Problems. And I'm using a notation which you'll all know from misleading advertising. I call it the not really star. It's the appending a little asterisk to the end of a statement that while it might be useful or convenient to believe it to be true, in fact it's strictly incorrect. During my talk, you can see the presence of that star to either be part of a regular expression or to mean not really. So I got the title of the talk from a quote from a guy called Jamie Zawinski. Some people, when confronted with a problem, think, I know, I'll use regular expressions. Now they have two problems. And there's some truth to what he says. Regular expressions can be very difficult, very dense and complex. And they can be a maintenance problem for any software that makes especially heavy use of them. So I've put down that Jamie Zawinski there is a nightclub owner, and you might ask, what's a nightclub owner got to say about regular expressions? Actually, he is a nightclub owner. He's more famous, however, for being a programmer of Emacs and of Netscape and Mozilla. But something he's ignoring is that if you've solved the original problem that you were using regular expressions to solve, then you need to deduct that from the two problems, and that leaves you with only one problem. And you might think, well, that's no good. I started with one problem and now I have one problem. What was the point? Well, this is what computer science is all about, replacing problems with other problems. Not really, no. What computer science is all about is replacing problems with other problems which are smaller. So as long as the problem of having regular expressions is smaller than the problem you were trying to solve, then regular expressions could be a great way of solving them. I want to convince you that you should know regular expressions, and I want to do this with a simple argument, and that's based on the fact that the probability that you'll need to maintain code that contains regular expressions is basically 1. All of the products at Atlassian have regular expressions in them, and you will be faced at some point with needing to understand how it works, and so there's going to be some use for it. I can't really go into the topic very deeply without mentioning the one true source of all that is good about regular expressions, Jeffrey Friedel's book, Mastering Regular Expressions, the OWL book. It's an awesome, very well written volume and has several editions now, good language specific details and lots of background information about how regular expression engines are implemented. It's actually quite an interesting topic. There's plenty of tool support for regular expressions. You probably use tools every day that have regular expression support in them. grep is the obvious one. It's a verb in its own right now. It means get regular expression. It also comes in a variation called egrep. Programming languages such as modern and scripting languages all have regular expression support. Java regex support is great. Well, it would be great if the syntax of regular expressions was better integrated into the syntax of Java, like it is with many of the scripting languages. As it is, Java regular expressions are captured as a string, and the problem with that is that the escaping mechanisms of the string and the limitations of string to be only a single line really interfere with the mechanisms of the regular expression language itself, and it restricts the ability to make effective use of them. JavaScript has good support for regular expressions. You should also definitely, if you're using IDEA, IntelliJ IDEA, you should definitely get the regular expression plugin. And I've heard that Regex Buddy is an awesome tool. It's a Windows commercial application. I haven't used it myself, but I've seen it used, and it has some pretty impressive features, such as debugging support. There are a lot of acronyms that go with regular expressions. There's the basic versus extended regular expressions that are implemented using NFAs and DFAs, non-deterministic finite automata and deterministic finite automata. There are POSIX standards. There's a lot of technical detail. I'm not going to be covering any of this detail, but you can certainly read up about it in the OWL book or in the man pages for the regular expression engines. Regular expressions have a little bit of a bad reputation. They are, I guess what I want to present them as is a dependable brand. You can certainly come up with regular expressions that are very difficult to use, they're very dense, and it may be necessary for the goals of the system, for the feature you're developing, for the bug you're fixing, to use difficult and dense regular expressions. The language seems to lend itself to difficult, dense expressions. And so given that, the way you should approach them is to slow down and to imagine them as a boiled down nugget of a page or more of code. You shouldn't just expect to see the line and understand it instantly. You'll need to go through it slowly. So that brings me to the aesthetic of regular expressions. Beauty's in the eye of the beholder, and much like bicycle shoes, regular expressions are a thing of beauty. So the first regular expression that you can learn, and very useful one, is the following. It's the dot followed by the star. That's just a period and asterisk. It matches anything. So regular expressions are a language to describe strings that are matched, and this particular example matches anything. Or does it? Actually, it matches anything and it matches nothing. If you were to give this regular expression the empty string, it would match it. There's nothing in the string, the input would be empty. However, this regular expression has no problem saying thumbs up, I match that. The reason is because the dot, while the dot character represents any character to be matched, such as an A or a C or a dot or a slash or any character in the input, the star character indicates, it's a quantifier. It indicates how many times the dot is to match, and it refers to 0 or more matches. So the dot star may match nothing because it matches any character 0 times. There is one thing that it doesn't match, however, and that's usually because of the way that the match request has been made. At the end of the line, the dot character normally is configured not to match. So if you're parsing or running through input that's line-based, as you frequently do with, say, Perl or awk, sed, the dot character in regular expressions is configured not to match the end of that line. So it will match a whole line and not the end of the line. So this brings me to something. This is an attitude you need to adopt when you're thinking about how to craft a regular expression. A regular expression must always match something. Well, that's not really true, but it's really important that you start with this thought. It's very difficult with a regular expression to specify what you don't want. Regular expression engines really want you to say what should be matched. So you think of it as a specification of the set of strings that will match the expression. You can't really refer to things that are not matched as easily. You'd be much better off writing that logic into your programming language, such that if the expression is matched, then don't do this other thing. First thing you need to learn about regular expressions is that there are simple characters that refer to themselves, that match themselves. The lowercase a matches a lowercase a. If you have a lowercase a in your regular expression, then that part of the regular expression will match only a lowercase a. Likewise for the other characters, including the space that separates the b and the slash. These characters are not special. They're not what are called metacharacters. They don't change how the match works. They're not like the dot or the star. They just refer to themselves. The next category I want to talk about is escape sequences. You've probably seen \n and \t in C or Java, and these are two characters when put together refer to another character, which is typically difficult to represent literally. The \n refers to a new line, the \t refers to the tab, and because you're using / in a special sense, / is therefore a meta character. In order to represent a \, you need to apply the same escaping behavior to it. So we do that by applying two \. That means that the two \ represent a single literal \. You need to remember that if you ever need to write a literal \. Likewise, any other meta character needs to have the \ prefix. So \* means a literal star. It doesn't mean 0 or more as it does when the \ is not there. You can also have hexadecimal, octal, and Unicode escapes to represent characters by their numeric identifier. So here's a set of meta characters, special characters that mean something in regular expressions that isn't themselves. These all need to have a \ put in front of them in order to represent them literally. If you don't do that, then they will have their special meaning, which I'll come to in a minute. The first group of meta characters are the quantifiers. You've already seen the star. That means 0 or more times. These tend to go after something else to modify how many times that something else is to match. If it's a single character, then the star means 0 or more of those single characters. Likewise, the question mark means 0 or 1 times. The plus means 1 or more times. Braces are used to specify how many times you want it to match. So here are two regular expressions, A star and A plus. I mentioned to you that the star means 0 or more times and the plus means 1 or more times. So in these two cases, the same input strings are matched. In the first case, the first A must match an A. The second A can match 0 or more times, meaning a string of, say, 3 A's will match the first A will match the first A, and the remaining 2 A's will be matched by the A star. Likewise, a single A can be matched where the first A matches and the second A matches 0 times. In the case of A+, it's exactly the same. However, the quantifier used explicitly states that there should be 1 or more A's. Here are some of the braced quantifiers. X brace 7 brace means match 7 X's. X in this case could represent any other regular expression, doesn't need to be just the X, but I'll come to more complicated ones in a while. The Z may match 6, 7 or 8 times. It's a range of times, 6 to 8. The W may match 0 to 8 times, and the T may match 6 or more times. So these are a great way of reducing the size of your regular expression, and by, in a highly expressive way, stating exactly how many times a given sub-expression must match. So I've explained what these single character quantifiers on the left mean, and I've explained how the braces work. And so on each side, left and right, you can see there is an equivalent. You'd usually prefer the single character in each of these cases, but they are equivalent. There's also character classes. These are a way of matching a single character. The single character is matched based on its presence or absence from a set of characters, and the set of characters is specified in the square brackets. So the first expression will match any of the vowels A, E, I, O, or U. Only a single one. The second character class will match either a double quote or a single quote. The long character class there will match any hexadecimal digit, upper or lower case. And down the bottom we've got a combination of a literal 0 followed by a literal X followed by a character class with ranges in it, meaning that the hyphen refers to any character between A and F, or 0 and 9, and so that character class is equivalent to the character class in the line above. You don't need to specify the entire, and you don't need to enumerate the whole set. You can use ranges of characters, and the ASCII values are used to map between the beginning and the end of the range. And at the end of the bottom expression is the one or more quantifier, meaning that the whole expression matches a 0 followed by an X followed by one or more hexadecimal digits. Character classes are a mini language of their own. They're a language within the language of regular expressions. They have different metacharacters. There are metacharacters that are only metacharacters within ranges, and there are metacharacters that are only metacharacters outside ranges. So, just to give you a composite example here, the expression, the regular expression there, contains the hat or caret character at the beginning. When it's at the beginning, what this means is a set that's been negated. It means I'm going to enumerate all of the characters that should not match. Now the entire character class will still only match one character, but it must match one character that is not contained within the remainder of that square bracket expression. So the characters then are open parenthesis X, pipe, Y, close parenthesis, or dollar. All of those, many of those, are metacharacters outside the square brackets, but inside they are simply their literal selves. And so this expression will match any character that's not one of those. The parentheses are used for grouping. So if I want to match a string that is foo followed by bar or foo without bar, I can put bar into parentheses and put the 0 or more quantifier on the end of it. That means only foo followed by an optional bar will match. The next one matches ho 3 times, ho ho ho, 3 times only. The next one matches a literal ampersand NBSP semicolon, 0 or more times. matches 0 or 1 time, an optional NBSP. And the last one is one large group with an asterisk at the end. That means 0 or more. And then within the parenthesis it contains a p tag, HTML here, followed by one or more NBSP semicolons, followed by a /p tag. Now the entire thing will match nothing because that would be 0 times that expression, but if it matches once or twice it must consist of a p tag followed by at least one NBSP followed by a /p tag. There's also an alternation operator, which is the vertical bar. This is used to separate alternatives that would be grouped together. So in the first case I can match Tweedledee or Tweedledum. In the second case I can match an ampersand followed by any of LT, AMP, GT, QUOT, and the entire thing must be followed by a semicolon. So it's interesting to note here that if these alternatives are single characters, then the expression in parentheses x pipe y pipe z will match the same strings as the character class x, y, z, namely a single character, either x or y or z. However, that is not the case if x, y, or z are not single characters. Character classes are only for characters, whereas the alternation operator may separate sub-expressions, which can be groups of characters or entire complicated regular expressions in their own right. Now, just to wake everyone up after going through a few of those, there's a little quiz. Now, because this is a recording, there's no point in me asking this. However, think of the answer in your head, and I will tell you the answer in a few seconds. How many characters are zero-width assertions? How many characters wide are zero-width assertions? Have a think about it. This is regular expressions. It's tricky stuff. May not be obvious. Actually, it's obvious. Zero-width assertions have zero width. They are 0 characters wide. Now here's some zero width assertions. Not really. These are not called zero width assertions. However, they are zero width and they are pretty much assertions. So I'm calling them zero width assertions today. The circumflex, the hat character, refers to the beginning of a line or a match area. The dollar refers to the end of the line. \b refers to the boundary, the zero width boundary between a word and a non-word. And the capital B refers to the set of characters that is the inverse of that set, such that it is not a word edge, such as between two word characters or between two non-word characters. And likewise, the left angle refers to a left word edge, meaning the space between a non-word and a word character, and the \right angle refers to the space between a word character and a non-word character. That's going left to right. Now you might ask what a word character is, and I'll come to that. So here's where each of those matches. The beginning of the line matches just to the left of the capital G in this input string. Likewise, that's a word boundary, since we've gone from not a word character, the beginning, to a word character, the G. It also matches the left edge of a word. Further along, the \b and the right edge matches just to the right of the N. The dollar matches just to the right of the comma. The \b matches between the y and the e, and of course in many other places. It's not the edge of a word character, not the edge of a word. It is two word characters, y and e, next to each other, and so the \B matches there. And then just to the left, so between the parenthesis and the s, matches the edge of a word character and the left edge of a word, because the parenthesis is not a word character. So here's where we talk about what word characters are, and these are character classes as well, but they have special symbols to represent them. So you frequently need to refer to digits. You can use a character class of square bracket 0 range 9 close square bracket, or you can use \D, which means the same thing. It's just a shortcut for that special category of characters. There is such a thing as a word character. This is defined as an alphanumeric character or underscore. That's upper and lower case, and the underscore, and the digits. A space character refers to a white space. This includes the little known form feed and vertical tab, as well as the usual backspace, new line, carriage return, tab characters. These are all inverted by putting them in capitals. Capital D refers to a character which is not a digit. \W refers to a character that is not a word character. So that's anything except alphanumerics and the underscore. \S refers to any character that is not a space character. Capturing and non-capturing groups. We've met groups, grouping. You can put parentheses around things so that you can put a quantifier on the end. But that's not the only effect of putting parentheses on. Most regular expression engines will remember each captured group at the end of the match, and you're able to use that memory to fish out different parts of that regular expression. This is extremely useful in creating ad hoc parsers. You're able to say, oh, this little bit here, I want you to remember that. But there is an overhead to remembering each group, and if you find yourself using parentheses to group things together, you'll sometimes see that you lose track of which group is which if you have a lot of parentheses. If you add a parenthesis in, you've shifted the group numbers all along. And that's why there's a different kind of parenthesis expression, which includes the question mark colon sequence that does exactly the same thing in terms of grouping, but it doesn't cause the regular expression engine to remember what was matched, which means that if you mix in plain parentheses, only the plain parentheses will be counted as matching groups. And each of these matching groups can be referred to within the regular expression, and usually within a replacement string, which is quite often what you want to do with a regular expression, is match something, and wherever you find that, do a replacement of it with something else. You can find that the capturing groups are very useful for that scenario. So there, the backslash and number. \1 refers to the first matching group identified by its opening parenthesis. \2, the second matching group. \3, the third matching group. There's also the concept of greediness in quantifiers. You need to know, in order to correctly craft your regular expression, you need to know what part of the regular expression is going to match what part of the input. So sometimes there are multiple ways it could happen. So the rule is that quantifiers mean as many as I can match, so that if they can, in the case of, say, an asterisk, If they can match, they will match. And only when it's found that later parts of the expression cannot match will the engine decide to go back and see if there's another way for that quantifier to match the input by taking less. In this case, it's a regular expression of dot question mark dot question mark. If I was to give that one character, which dot would match it? The first dot can match it 0 or 1 time. The second dot can match 0 or 1 time. That's the role of the question mark. But if I give it one character, it could, in theory, match the first dot 0 times and the second dot once. Or it could match the first dot once and the second dot 0 times. But because of the principle of greediness, the rule is that the first instance should match as much as it possibly can, and only fail to match if it prevents the entire regular expression from matching. So if I give this regular expression a single character, it will be the first dot that matches that one character, and the second dot will match 0 things. So here's a use of the back references. Here is a regular expression that contains a lot of literal characters, mostly readable. It matches a phrase. If you have a and then some word, comma, can I borrow your, and then an expression that's derived from whatever matched in the parentheses, followed by a literal question mark. So the green string there, if you have a Ducati, can I borrow your Ducati, will match, because the \1 will match the same word as the parenthetical expression \W+, which means one or more word characters. Remember, word characters are upper and lowercase and numerics and underscore. However, the second string will not match. If you have a virus, can I borrow your Ducati? The reason it won't match is because virus will match the parenthesis expression. However, the match will fail when it gets to Ducati, as it finds that the D is not the same character as the V that matched in that parenthesis expression. The opposite of greediness is laziness. What if you don't want your star to match your whole string? What can you do? Well, you can simply add a question mark on the end. So star question mark is another quantifier. Plus question mark and question mark, as well as the brace min max range brace question mark. All these are quantifiers, but they match as little as possible. So in the previous case, I asked about the dot question mark. If we'd written dot question mark dot question mark, the first dot would not have matched because it doesn't have to. So these are also known as reluctant quantifiers. They choose to match as little as possible. If the regular expression engine can continue without matching, it will try to. Now here's a little snippet that shows you the power of regular expressions and to some degree the power of Perl. Perl allows you to specify a script directly on the command line. That's what the -E flag does. And in single quotes I have there a Perl statement. I'm also passing the -P option to Perl, which is a special kind of magic that makes it work a little bit like awk, in that it will loop over all of the input, printing every line after it executes the given statements that were provided in the script. And those are on the command line. So what we have there is an s/foo parenthesis, something in there, /bar, \1/g, semicolon. The semicolon is the statement terminator in Perl, so that just indicates the end of the statement. The S is a substitution which indicates that the regular expression that exists between the first slash and the second slash should be matched against the input, and anything that matches should be replaced by the expression, the replacement string, between the second and third forward slashes. So anything that doesn't match isn't replaced. It just goes out the output. So a string like foo will not match because the regular expression says foo followed by 3 word characters. And those 3 word characters that matched are remembered as match group 1. The replacement in the case of foo bar is foo matches followed by 3 word characters, which are in this case bar, and the replacement string bar plus whatever matched in the parenthesis, which is also bar, results in bar bar. Food does not match because there must be at least 3 word characters after foo, so it goes through unchanged. And foodie matches because there are 3 characters after foo, and foo is replaced with bar. The G in this indicates that the substitution should occur as many times as it can. If it was to match twice in one line, then it would replace twice in one line. In these examples, it only ever matches once. So outside the regular expression language, there are configuration options to give to the matching process. I mentioned these earlier, such as the ability to match the end of a line with a dot, and there are also some others that are easy to understand, like case sensitivity. These usually have character identities. The characters given there indicate these modifiers, and they configure the regular expression engine to be in case insensitive mode, or matching the end of the line mode, or multi-line mode, or comments mode, which is an example I won't go into. But within the regular expression itself, you can turn these modifiers on and off, such that case sensitivity happens temporarily within the regular expression and then is turned back off to become case insensitive again. It's an extremely powerful feature, not often used, but it does enable you to get out of a tight jam. There's also mechanisms for turning off the metacharacter, the special metacharacter identities. If you were to put a \Q, \Q into your string, then what would have been a metacharacter following that will just represent its literal self, such as a pipe, until the \E sequence, which turns the metacharacter special values back on again. There are some advanced topics here. This is where you get to specify what you don't want, or to make assertions, what really are called zero-width assertions. Make assertions about the string without actually matching that part of the string. And the distinction is something that really only makes sense once you start understanding how the regular expression engine works. And that is that it's like a little machine that runs along your string and making assertions about the contents of the string as it goes. In the first case, I've got a regular expression, foo, paren, question equals bar, close paren. And the expression there, the paren question equals is a positive lookahead assertion. What it means is match the sub-expression foo, except ensure at the point of matching foo that bar is following, but don't match bar. Likewise, you can have a negative lookahead assertion where you say match foo, that sub-expression, could be complicated sub-expression, only if it's not followed by the sub-expression bar, but don't match bar, match only foo. So as long as there's no bar there, foo will match. There's also positive look behind assertions, such that you can say only match rocks if it is preceded by regex. And there's negative look behind, which in these cases means only match sucks or sucks, two spellings of sucks, if it's not preceded by bamboo, clover, or jira. Now, performance is something that, to be honest, you don't think about a lot with regular expressions because you don't need to think about a lot. But every so often, you get into a situation like this poor guy on the web, and you need to understand why performance is poor. This is one of those cases where you need to understand what's happening inside the regular expression engine. Most performance problems in regular expressions have to do with backtracking. Backtracking is when a regular expression matches through the string and then reaches a part of the expression that cannot match the input. If there were quantifiers or alternates in the preceding matches, that means that there's an alternate way to match the regular expression, and what the engine does is goes back, spits out the characters that it matched, and tries to match the input using one of the different alternatives. And in this case, we can see that there's a parenthesis with matching a word character 0 or more times, followed by a space character 0 or more times, all matching 0 or more times, followed by a literal string, presumably this poor guy's name, and then the same thing after his name. Now, quite clearly what he's trying to do is match his name somewhere in the document. The problem is that there are too many ways for the input to match the document incorrectly. So what the regular expression engine does is, first character, it's a word character. Well, it will match. Second character, another word character, it will match that same \w. It will keep matching word characters because it's greedy until it hits a space when the word character won't match. Then the space will match the following part of the regular expression. And then that sub-expression will match, so that sub-expression will match the first word followed by a space. Now that entire thing can match multiple times. So when it gets to the end of that sub-expression, it can go again. It reaches another case where there's a word character and it can match the W again. It can keep going through until it's matched all of those words, including, presumably, if it's present, Zlatan Ibrahimovic, because they're just word characters as well. So it will match his name. It will even match the entire input document, assuming it's only consisting of word characters and spaces, whether his name is in it or not. However, once it gets to the end, and it pops out of the end of that word space star parenthesis expression, it will need to match a space. Well, if the document ends in a space, it's already matched that space with the parenthesis expression. So it'll need to backtrack. We'll need to spit that space out and attempt to rematch at that point, which it can do. Then it will match the space at the end of the document, and then it will say, oh, no, there's supposed to be a Z here. Well, I'm going to have to back up again. And it will keep going backwards, spitting out input characters and attempting to rematch the input until it finds a Z. Then it will fail to find an L, presumably because it's matching a word like zero or zoo, and any other word that contains a Z. And it will continue spitting out input until it finally matches, if it ever does, the literal string Zlatan Ibrahimovic. And then at the end, it has to do all of that matching again. So the reason why this guy's computer is into 100% CPU power and not closable is because he has defined a metric buttload of ways that his regular expression can incorrectly match the input, almost. So left to right through your input, you want to reduce the number of ways that your regular expression can match the input. And you want to watch your use of quantifiers. Sometimes, and in fact perhaps in this case, it would be better to use non-greedy quantifiers. Or maybe he could use a positive lookahead assertion on those first quantifiers, in that it will only match them if it's followed by the literal string. Now here's a depiction of the backtracking process as represented in this Windows program, Regex Buddy. You can see the regular expression is regexp ? Regular expressions are sometimes contracted to regex or regexp. So the P is optional with the question mark, 0 or 1, followed by buddy, followed by space is, space, followed by one of 3 alternatives, which is awful, acceptable, or awesome. On its way to matching awesome in the input, it will fail to match awful and have to backtrack and try awesome, but only once it's done the first 2 characters. And you can see what's happening here if you look at the lines in the debug output, lines 19 and 21, where the fact that the engine is backtracking and spitting characters out is represented in the output. So if you have umpteen squillion ways of matching the input incorrectly, you'll have umpteen squillion backtrack situations in your execution of your expression. So there's also a feature called atomic grouping, which I don't want to go into in too much detail because it's actually quite tricky. Atomic groupings are like a commit in a transaction where you say if you do match, then lock that in and don't backtrack. There's also a bit of a problem, rough edge in the regular expression language, in that it came from an era before Unicode where all the world was ASCII. And so what I was showing you earlier with the word characters and the ranges A to Z isn't going to work in a Unicode input, because A to Z are just ASCII characters and your input may be Unicode, which includes all sorts of other characters that are considered parts of words. There are many modern standards efforts within regular expressions that are attempting to solve this problem, and to a greater or lesser degree they have some workable solutions. I'll let you read the manual for the details of that. Here are some character classes where you can specify that you want a Greek Unicode block character, or an uppercase letter, or a currency symbol. And there are plenty of these symbols to refer to Unicode character classes. There's also a problem in regular expressions called the leaning toothpick syndrome, such that the fact that you're using forward slashes to quote your regular expression, as you can in JavaScript or Perl or many other languages, is more of a hindrance than a help. And where Java string-based quoting would actually not suffer so much. And that if you've got a URL that you want to match, it contains lots of forward slashes, but your forward slash is your delimiter, so you'll need to escape that to make it a literal forward slash. So everywhere, including in character classes, where you have a forward slash, you'll need to put a backslash in front of it, which makes a total mess of a URL, such as in this case. These are some of the some of the topics I haven't covered. If you're a regex nut already, then you probably don't need this talk, but bear in mind that there's still some more magic to be learned. There are different kinds of quantifiers. There's more trickiness in the way that character classes can be specified. There's plenty of stuff in Perl that you can do, and there are symbolic names for character classes that are part of the POSIX standards that I haven't mentioned. And to finish off with, here's a little regex puzzle that I think you should be able to handle if you've absorbed any small part of this talk. It's a regular expression. It's a geek joke, geek t-shirt joke. So see if you can work it out. The forward slashes are just the delimiters, so they're not part of the actual regular expression, but what they do indicate to a passerby, of course, as everyone knows this stuff in the street, is that it is a regular expression you're talking about. So just take off those forward slashes off the front and back, and you're given a parenthetical expression with, if you look through it, a single vertical bar in it. So there's an alternation. So it's either the thing to the left of the vertical bar within the parenthesis or the thing to the right. So on the left you have two B characters. So the regular expression will match two B's. And the other side of the alternation is first a character class, which is specified by negation. The hat character indicates that you're specifying what you don't want in your character class, and that is a B. And the braces with the 2 in it indicate that you're interested in matching 2 only of those. So it's a not B 2, not B's. Anyone got it yet? It is Shakespearean. It is Hamlet's to be or not to be. And on that note, I hope you've enjoyed this topic, and I'm interested in all feedback, and I look forward to doing something in a similar vein in the near future. My email address is chris@atlassian.com.